Welcome to another episode of Advantest Talks Semi, the podcast where we dive into the hows and whys of technological progress and the waves they create in our world. I'm your host, Keith Schaub, and today we're hitting the road with Fabio Marino, Managing Director at CREA from Advantest in Italy, to talk about the automotive semiconductor industry and how electric vehicles, EVs, have seemingly electrified the industry. Over the past 10 years, EVs have transformed from a niche to a mainstream market. In 2022, EV sales were up as much as 50% over 2021, and there are now more than 26 million EVs in the market. Some analysts have estimated that by 2032, as much as 2/3 of all vehicles sold in the US will be electric, and several major car companies have announced they will stop producing gas engines by 2035. What fueled this shift? What challenges and opportunities does it pose for the semiconductor industry, and where do we go from here? Let's plug in and get charged up for an electrifying conversation. Hi Fabio, welcome to Advantest Talks Semi.
Hi Keith, really pleasure being here.
It's interesting to see how we've had electric vehicles for over 100 years, but only in the past 10 years has it really become mainstream. And so I wanted your take on what are you seeing in the industry that's sort of causing this shift to move from gas-powered engines over to EVs?
Well, we all understand how important it is to protect our world. Moving to green energy is somehow a road we all need to walk. And Advantest, since many years, is promoting several initiatives also in this direction. And going to electrical vehicle is exactly the right thing to do in order to minimize the air pollution and protect our world. So that was stimulating this growth.
Fabio, what are some of the current trends that you are seeing in the EV market?
But the main trend I see at the moment is really leading the electrical vehicle market. So all the companies are really racing to gain the market share there. So this power semiconductor market is expected to go from 150 million in 2022 to 520 million in 2030. I'm talking about testing market, right? Not semiconductor.
So a 5x growth?
5x growth, yes. And testing market normally is in the range between 1 and 2.5% of the market. So you can calculate how big the market is. And this is driven by electrical vehicles. So this is the trend I see is, first of all, for companies to win market share in that market. And I see Chinese companies are investing a lot, and companies like, for example, BYD in China overtook even Tesla by far, by 2 times already in a couple of years.
Thanks, Fabio. What about the technological innovations that have been occurring in the industry? What's been going on in the past, let's say, 7, 8, 10 years that is helping that transformation?
So this kind of power semiconductor, most of them are known as Discreets. They are there since many years. They were pretty common in the white goods, like washing machines, for example, refrigerators, but they were really a niche for the market because very low average selling price components, very cost sensitive, so not really appealing in the market. In reality, those devices are now back into the game thanks to the need to go to green energy, to electrical vehicle. And we are using exactly the same components from the past. On top of those components, which are the typical IGBT, the typical power MOSFET, power BJT, but on top of those components, recently silicon carbide and gallium nitride came into the game. Those are 2 new technologies made of wide bandgap materials with some specific features that empower the specification of those devices. But this is the only technology that came over the last few years. For the rest, we are talking about very established technology.
Fabio, you mentioned several technologies like IGBTs, insulated gate bipolar transistors, and silicon carbide. And there's also gallium nitride or GaNs. Can you quickly explain and contrast these new frontier technologies for us?
There is a substantial difference between silicon carbide and gallium nitride. From technology perspective, the gallium nitride is much more similar to the standard silicon. So this makes this technology much more mature and easy to, to handle by the traditional semiconductor company. And also, so integration, for example, will be much easier on gallium nitride. The other topic is that gallium nitride is also a wide bandgap material. It is much faster, so allows a really fast operation switches. So this makes this component very good for switching, so for DC-DC converter, for example, and even the size is smaller because of the higher frequency. So this is perfect for small components like mobile phones, for example. The limitation or the other difference between the silicon carbide and gallium nitride is on specification. So normally gallium nitride, which is faster, can go up to 650 volt. There are some experiments to go beyond 1000 volt, but it's still on the niche side compared to the 650 volt. While silicon carbide can go up to kilovolts, right? So even the field of application is different. So normally we tend to put together silicon carbide and gallium nitride for power electronics, but these address two different kind of market. Silicon carbide is more focused on electrical vehicle. Gallium nitride is more focused on DC-DC converter for this power greedy application. The main difference is in the power that those devices can handle, both in terms of voltage and current. There are standard silicon components that can handle high voltage but low current, and vice versa, high current and low voltage, but in reality those components handle mid and low power. The power semiconductor can handle both high voltage and high current, resulting in a big amount of energy.
I'm assuming then there are specific test challenges that go along with that because of the extreme high voltages and the high currents.
Your assumption is correct, Keith. Actually, the big challenge is in the dynamic test. So for this kind of components, there are two kinds of tests, static and dynamic. The static test falls in what we can call low power test because the switch, the device is either on or off. And in that condition, the overall power is low because can be high voltage but low current, or high current and low voltage. So in this case, the total power would be low. But during the dynamic test, which tests actually the device under its transient from on to off or from off to on, the amount of energy into the game is very high, even if for a very limited amount of time. And this is the big challenge.
I guess we're talking about the instantaneous voltage changes and the instantaneous currents. Is that correct?
It is correct, but both occurs at the same time. So while the current is flowing, very high current is flowing, the voltage is also going high, and the combination results in a high power.
And what sort of voltage and current levels are we talking about here? I've seen numbers that are in the thousands of volts and the hundreds of amps.
It depends on the final application. It can be for train, for example, or for electrical vehicle or for photovoltaic cells. But actually, we are talking about 10 kilovolt at 10 kiloamps, for example. So we are talking about an extreme huge amount of current and voltage.
How many probe tips apply the current to the wafer probe solution?
It sounds like a surprise that a three-pin device, three-pad device and a bird eye needs 3,000 needles in a probe card for a single site test. And this is due because each needle can only stand a limited amount of current, normally in the range of 1 amps. But we have test conditions for example, for short circuit where we provide 3,000 amps. And to do that, you really need 3,000 pogos on the probe card. This makes probe card business also very interesting because those consumable parts are very expensive. The testing is pretty much robust, but for good parts, the testing time is so limited that this does not represent any problem. For failing parts, anyway, those parts cannot really stand that current and immediately show problems that our probe card interface technology detects, protecting then the full equipment.
That brings up testing challenges with that high of a voltage or that high of a current. How do we actually test those moving from a niche market to more of a high volume mainstream market?
So first of all, the first challenge is the capability, right? Tester capability. So not all the tester equipment are able to test those devices during dynamic behavior. In CREA, how we developed a proprietary technology that allows that test. We can test those dynamic specifications thanks to our low strain inductance technology and the probe card interface technology.
Give us the background on CREA. Where did it come from? How did it get started? And what's their specialty?
CREA started in 1992 as an engineering company developing a specific product based on customer demand. Over the years, the demand was going more from an engineering need to a production need at a very high current and very high voltage. And CREA developed this technology year by year. Currently, the product we have top-notch technology in terms of dynamic test of power semiconductor. In order to be successful, CREA had to face difficult challenges for dynamic test because, as I said before, dynamic test implies huge energy. And with this huge energy, parasitic inductance, parasitic capacitance come into the game and can impact testing quality and can even break the test equipment. That was the first challenge CREA had to face. And over time, we developed the low strain inductance technology in order to minimize these parasitic values to the point that we can test those devices at very high current and voltage. The new trend is anyway to move from package test to bare die test.
Why is that?
The main reason for that is package test is much simpler, but the drawback is that each package contains 6 to 48 single switches. And if one of those switches is broken, then the entire package has to be trashed, actually, with a big amount of money wasted. Customers are now asking for bare die test in order to screen the parts before assembly and minimize the cost impact on the package side. This is the reason for that. But unfortunately, this brings another big challenge in the testing arena, which is the bare die test, where you need also a probe card to perform the test. And if something goes wrong or if a device is broken, the big amount of energy in the tester breaks the probe card, the chuck, the die, and even the tester. And that was the challenge CREA had to face at the beginning.
How do we deliver kiloamps or kilovolts through a probe card reliably and efficiently?
Sure. Actually, the solution for us was to develop a probe card interface, which is a piece of hardware that is in the middle between the tester and the probe card. This hardware actually monitors the current distribution for each and every needle or for each group of needles in the probe card. By doing that, we can predict if something is going wrong. If there is an abnormal current distribution, we can immediately switch off the tester and in this way protect the equipment and the probe.
EVs have fewer parts than combustion engines. I've seen where EVs typically have around 13,000 parts, where combustion engines have 33,000 parts, so almost 3 times fewer. or a third as many moving parts, which also reduces maintenance costs and repair costs and helps fuel the transformation and the interest in EVs. Is that something that you see when you talk to power semiconductor manufacturers?
Actually, this is a good point because normally our customers or even automotive manufacturer, they don't highlight this point that much, honestly. What this reduction in the moving component is bringing to the game is that many more companies are now capable to manufacture electrical vehicles because actually the electrical vehicles removes the technological barrier of thermal engines and goes to an electrical vehicle technology which is much easier. Many more companies, even for example companies traditionally in the mobile business, now they are willing to build electrical vehicles. They're moving in that direction.
Basically, the barrier to entry for automobile manufacturing is now much lower, so we have a lot more players in the market. That's going to be pretty interesting for competition, but also good for consumers, I guess.
Exactly. This will dramatically reduce probably the costs for electrical vehicle rather than having much less components on it.
What's coming in the future? New needs or new capabilities that are required to address this market?
Yeah, there are a couple of things that I see. One is from technological perspective is to make the silicon carbide technology mature enough for this market because this gives big advantages in terms of component size and thermal dissipation power. Silicon carbide is a wide band gap material, and by definition, those materials they can stand higher voltage, higher current, can be smaller and have much better thermal dissipation powers. This is the first challenge because this technology is not mature yet. Production yield is not big, so this is a big opportunity for testing companies because the yield is not so high. But of course, semiconductor company needs to make this technology mature to make the business sustainable for them. And this is the first challenge. The second technology challenge is integration, as you mentioned. So we foresee intelligent power module to grow a lot, integrating power and some digital control or even mixed signal acquisition, for example, in a single package or in a single integrated power module.
You mentioned the silicon carbide maturity, and it's still a maturing market. Can you talk about what are some of the things that's causing that, and what are some of the things that need to happen in order for that to mature?
Yeah, semiconductor companies are investing. You may read on news papers that several companies are investing in silicon carbide factories. So the first problem silicon carbide has is, how to say, very tough material to handle. In a sense that the standard silicon wafer technology does not apply as it is for silicon carbide. You need different technologies. It's completely different from silicon. So even singulating the die of a wafer can have a big impact on silicon carbide. And also the wafer size at the moment is limited to 6 inches, so while on standard silicon you can have 12 inches wafers. These are all the barriers that semiconductor manufacturers are facing now and need to manage in order to make this technology mature.
The automated tools that we have in the factory cannot handle the new silicon carbide. Factories and companies are retooling for this new material, but at the same time, they're getting the boost from the market, which is fueling that investment.
On the integration challenge, I think we are ready.
The main takeaway is we're not a bottleneck. Our technology is essentially in place.
Correct. You said a very important thing, Keith. We are not a bottleneck. So if I look at the entire test line chain, where we need probe card, we need probers, we need handlers, I see that probers are not even available in the market yet for dynamic test, only for static. Handler have very long lead time. There are a few handling companies for bare die that have more than a year lead time for the equipment. And probe cards, there are very few vendors and are very expensive. So tester side, it's absolutely off the shelf, available with the right price, market price, and the right specs.
So Fabio, I want to thank you for coming on Advantest Talks Semi and looking forward to the next podcast about automotive power semiconductors. Thanks, Fabio.
Thanks, Keith. It's been a pleasure being here with you.